This is the 11th video in a series devoted to differential equations. And in the previous video, we looked at how to solve every second order homogeneous linear differential equation with constant coefficients. We were able to solve all of them. And now we're going to look at their non-homogeneous counterparts, and we're going to look at a special case of their non-homogeneous counterparts. And in particular, we'll look at how to solve differential equations of the form ay double prime plus by prime plus cy equals e to the kx times p of x, where p is some polynomial. But before we start looking at these types of examples and coming up with a general strategy, we need to look at a general theorem. And this theorem will tell us the overall shape of solutions to differential equations like this. So let's look closely at the following theorem. So we want to suppose that we have functions p, q, and f, and they're continuous on an interval a, b, and that y sub p is a solution of the differential equation y double prime plus p of x y prime plus q of x y equals f of x. So that's a linear second order differential equation that's non-homogeneous. It doesn't have constant coefficients though. Then next, we'll also suppose that y1 and y2 form a fundamental set of solutions to the corresponding homogeneous differential equation. So we just replace f of x with 0. Then any solution of our original differential equation must be of the following form. So y has to be yp, that particular solution, plus c1 times y1 plus c2 times y2, where c1 and c2 are real numbers. So if you've taken a linear algebra class, and generally you take a differential equations after a linear algebra class, this should look fairly familiar. For when you're solving non-homogeneous linear equations, there's always a particular solution as well as a homogeneous solution. That's exactly what's happening here. Yp is like our particular solution, whereas c1y1 plus c2y2 forms our homogeneous solution, or our corresponding homogeneous solution. And that's because it's a solution to the corresponding homogeneous differential equation. Okay, so that being said, let's look at the proof of this theorem, which isn't quite as bad as it might seem based on the fact that this is quite a long statement. Okay, so let's suppose that y is a solution of our orange differential equation. And by orange, I mean this thing that's pointing to this brown box. So it's a solution to that differential equation. And now what I'd like to do is consider y minus yp. So the difference between the particular solution that we know and this new solution y. And what we'll do is put that into our differential equation or into our differential operator and see what happens. Okay, so that'll give us y minus yp double prime plus p of x times y minus yp prime plus q of x times y minus yp. So maybe I'll put a note here because this is like a calculation that's going to lead us towards the final result. Okay, but now by the linearity of the derivative and the second derivative and moving some things around, we can write this as y double prime plus p of x times y prime plus q of x times y minus the quantity yp double prime plus p of x times y p prime plus q of x times yp. Great. But y was a solution of that brown box differential equation, which tells us that all of this stuff, which I'm underlining in blue, condenses down to the function f of x. And then yp was also a solution to that brown boxed differential equation. So that tells us that all of this stuff, which I'm underlining in purple, also condenses down to the function f of x. But that means that we have f of x minus f of x, which is clearly 0. But that means that y minus yp is a solution to the corresponding homogeneous differential equation. So I'll maybe color code that as this yellow box right here, and I'll put a yellow star right here. So a solution of that differential equation. But we know that y1 and y2 form a fundamental set of solutions. Remember, a fundamental set means they span all solutions and they're linearly independent. We'll use the fact that they span all solutions. So this is a solution. We know that y1 and y2 span all solutions, so that means y minus yp must be a linear combination of y1 and y2. In other words, y minus yp equals c1y1 plus c2y2. And finally, the last step is just to add yp to both sides, and we end up with y equals yp plus c1y1 plus c2y2. But that's exactly where we wanted to end up right here. Okay, so the big takeaway here is, in order to find a solution to a non-homogeneous differential equation, it's often useful to find the solution to the corresponding homogeneous differential equation and then focus on finding some particular solution, and then after that you can write down your general form. So obviously from last video, we know how to find the solution to the corresponding homogeneous differential equation in this case, where we have constant coefficients. So that means all we need to do is focus on finding the particular solution. And that's exactly what we'll do. So now that we know the general shape of solutions to these non-homogeneous differential equations, let's talk about how we can find the particular solution. And we'll have 3 cases here, just like we had 3 cases in the previous video, although these cases are a little bit different. So we're going to start with the following ansatz, and that's just really a fancy math word for an educated guess. And that is, we should have a solution, a particular solution, which is a similar form to the output over here. And that's because if we take derivatives of e to the kx times a polynomial, we always end up with e to the kx times a polynomial. And so that means that this left-hand side will turn into a linear combination of e to the kx times polynomials. And then maybe we could tweak the coefficients on that polynomial in order to make it match with this right-hand side. Okay, but that's just an educated guess at this point. We'll see that this is a bit trickier in some special cases, which we will see. So let's look at some leading examples. So let's start with y double prime minus y equals 2x squared plus x plus 1. And you might immediately say, hey, that's not of this form over here, but it actually is of this form. Notice it's this form where k is equal to 0 because we would get e to the 0, which is 1. So it's important to look at these as well when we have our forcing function. Recall that that's the name of the function over here, is just a polynomial. We can view that as a special case of this more general setup. Okay, so let's immediately notice that if we look at the corresponding homogeneous differential equation, y double prime minus y equals 0, which has a corresponding polynomial of r squared minus 1 equals 0, which has roots 1 and minus 1, we get that the homogeneous solution is c1 e to the x plus c2 e to the minus x. So we went through that a bit quickly, but that's based off of what we did on the previous video. So that's the homogeneous part. Now we just have to find the particular part. And by this educated guess over here, it should be e to the 0x in this case times a polynomial. And now we just have to determine the degree of that polynomial. So let's maybe put guess right here. We're making our educated guess that yp should be equal to just some polynomial. Again, to reiterate because k is equal to 0 in this case. Now, what should the degree of this polynomial be? Well, notice we've got a second derivative. That will lower the degree by 2. We have no first derivative, but we have a 0th derivative, the original function, which doesn't lower the degree at all. So, since we've got a second degree polynomial over here, it stands to reason that we should guess a second degree polynomial for our solution, and that's what we'll do. So, a general second degree polynomial looks like capital AX squared plus capital BX plus capital C. We just don't know the coefficients yet. And in fact, this method that we're exploring here is sometimes called the method of undetermined coefficients, because we make this educated guess as to the general form, and then we solve for the resulting coefficients. Okay, so now our game will be to plug this function into our differential equation, tweak A, B, and C until we've got a particular solution. Okay, so we're going to need y double prime, so let's calculate yp prime, which is 2ax plus b. That means yp double prime is just 2 times a. Again, that's just from derivative rules. But now we want to look at yp double prime minus yp. So that's going to be 2a minus ax squared plus bx plus c equals 2x squared plus x plus 1. So we're imposing the condition that this yp is a solution to our differential equation. And that sets up the following equation, which is really the important equation to look at in this case. And that would be this 2a minus that polynomial equals 2x squared plus x plus 1. But now let's simplify this left-hand side a little bit. So that's going to give us negative ax squared minus bx, and then we'll have plus 2a minus c, and we know that must be equal to 2x squared plus x plus 1. Okay, so again, this is maybe a rewriting of that equation. And now from here you do a strategy that's similar to partial fraction decomposition, and that is you set coefficients of each power of x equal to each other on each side of the equation. So we'll get an x squared equation, an x equation, and then a constant equation. I'll just put a 1 next to that. So the coefficient of x squared on either side will be negative a and then 2. The coefficient of x on either side will be negative b and 1. Notice this immediately tells us that we know that a is negative 2 and b is negative 1. So that's good news. We already know those coefficients. And then the constant term on either side will give us 2a minus c from the left-hand side, and then the number 1 from the right-hand side. So let's see, 2a is negative 4. We add that to the other side and we'll get 5. But negative c is 5. That means c is equal to negative 5. So now we've trimmed down and gotten all of our coefficients. But that tells us that we can write our final solution. And our final solution will be this yp that we just determined with the following coefficients plus our general homogeneous solution. So in other words, we have y is equal to, let's see, minus 2x squared minus x minus 5, and then plus c1 e to the x plus c2 e to the minus x. So that would be our general solution in this case. Okay, let's move on to another example. For our next example, we'll look at the differential equation y double prime plus y equals e to the 2x. And so, like we did before, we need to look at the associated homogeneous differential equation. That's y double prime plus y equals 0. But we know the solution to this, which I'll call yh, is c1 cosine x plus c2 times sine x. And that's because the associated polynomial r squared plus 1 has solutions I and minus I. And again, that's built off of what we did in the previous video. Now we'd like to make a guess for the particular solution just like we did. And in this case, keeping in mind that our educated guess, our ansatz over here, is that it should be of the form e to the 2x times a polynomial. We just need to find the degree of that polynomial. But notice here, the degree of the polynomial is just 0 because we have a constant times e to the 2x, the constant which is the number 1. So it stands to reason that we should have a constant polynomial multiplying into this e to the 2x as well. And that, in fact, is what will work. So we'll use just a to be that constant polynomial. Now we'll calculate yp prime, which is 2a e to the 2x, and then yp double prime, which is 4a e to the 2x, and then plug this into our original differential equation and see what that leaves us with. So we'll have yp double prime plus yp. So in this case, we'll have 4a e to the 2x plus a e to the 2x equals e to the 2x. So the first thing that we can do is divide by e to the 2x to get that out of there. Or just think about extracting the coefficient of e to the 2x. That tells us that 5a equals the number 1. Or in other words, a is equal to 1 over 5. Great. But that means we've got our particular solution, we have our homogeneous solution. So putting this all together, our general solution will be 1/5 e to the 2x plus c1 cosine x plus c2 sine x. So that would be our general solution in this case. And I think after those two examples, we're ready to write down the first case for our general solution for differential equations of this type. Now we're ready to write down the first case of kind of the summary of this video, which is the format for the particular solution to the following non-homogeneous differential equation. And what we have is that yp, that particular solution, should be of the form e to the kx times q of x, where q of x is a polynomial with the degree of q equals the degree of p if k is not a root of ar squared plus br plus c equals 0. So it's not a root of the polynomial which is attached to the corresponding homogeneous differential equation. So we saw a couple of examples of this. I'd like to do a couple of setups. We won't finish this off because really the finish of all of these problems is pretty similar to something that you've done in like a previous class. I think the setup is important. So here's what we've got. We've got y double prime plus 2y prime plus y equals 3x e to the 5x. So now we first check that 5 is not a root to the polynomial corresponding to this differential equation. So that'll be 5 squared plus 2 times 5 plus 1 is not equal to 0. So that means this setup case that we have over here is good to go. That means an appropriate guess for our particular solution would be a linear polynomial times e to the 5x. That's because this polynomial is degree 1. So I'll just write ax plus b times e to the 5x. And then you would determine ax and b by taking the derivative, the second derivative, and building a system of equations, which, like I said, I'll leave for you. Then our next example to set up is y double prime minus 7y prime minus 8y equals x squared plus x times e to the minus 3x. So again, we need to check that negative 3 is not the root of the polynomial corresponding to this differential equation. So that means we need to look at negative 3 squared minus 7 times negative 3 minus 8 times negative 3 and see that that is non-zero. So in other words, like I said, negative 3 is not a root of that polynomial. So since it's not a root of our polynomial, this original case, we don't know the other cases yet, but this original case is satisfied and we can write down our appropriate guess. So our appropriate guess will be yp is equal to a general quadratic polynomial. I'll write that as ax squared plus bx plus c times our e to the minus 3x. And then you would want to take the derivative of this, so yp prime. So this is going to be quite lengthy, but really it's just a matter of good bookkeeping. So yp prime would be something like 2ax plus b times e to the minus 3x, and then minus 3 times ax squared plus bx plus c times e to the minus 3x, where I use the product rule there. And then you could maybe collect terms if you wanted to. So notice you'll have minus 3ax squared. That'll be our x squared term. Let's see, our x term will be plus 2a minus 3b times x. And then our constant term is b minus 3c. So that's all times e to the minus 3x. So that's yp prime in this case. And then you would want to calculate yp double prime and then put it into this original equation and solve the resulting system of equations for a, b, and c. So I'll do some examples of this later, but if you want to see these examples worked out super carefully, check out the complementary problem video that comes after this video. Okay, so now let's look at a leading question, which is really set up by this not here. What if k is a root of this polynomial? So now let's look at a leading example where this first case does not apply. So we've got the differential equation y double prime minus y prime minus 2y equals e to the 2x. And I say that this does not apply because notice that 2 is a root of the corresponding polynomial. But since 2 is a root of the corresponding polynomial, we know that e to the 2x is a solution to the corresponding homogeneous differential equation. That means if we plug in something times e to the 2x into the left-hand side, everything just cancels out. And the fact that everything just cancels out, that means it can never be equal to e to the 2x, and that would be problematic. Now, in fact, we have a general form for our homogeneous solution of c1 times e to the 2x plus c2 times e to the minus x based off of what we saw in the previous video. So all of this boils down to a multiple of e to the 2x is not a good choice for a guess here. And notice that a multiple of e to the 2x is what this would tell us. So we need some sort of other strategy. And we'll find that other strategy by making a substitution. Let's say y is equal to e to the 2x times z. And then what will that do to our differential equation? So that means that y prime is equal to e to the 2x times z prime plus 2 times e to the 2x times z, and then y double prime is e to the 2x times z double prime plus, let's see, we'll have 4 e to the 2x times z prime plus 4 e to the 2x times z. Great. So I won't check that carefully, but that's what you get if you take the derivative a couple times using the product rule. Okay, so now let's plug that into our original differential equation and see what happens. So our original differential equation, y double prime minus 2 times y prime minus 2 times y. So I'll go ahead and factor an e to the 2x out because that's a common term in all of these. And then let's color code some things. So in inner yellow parentheses, I'll put my y double prime term. So that'll be z double prime plus 4z prime plus 4z. Great. So that comes from my y double prime. Keeping in mind I factored this e to the 2x out. And then from that, I need to subtract y prime. Y prime is this thing right here, so let's color code that with red parentheses. So I have z prime plus 2z, okay? And then finally, I have minus 2 times y. So that'll just be minus 2 times z. then maybe I'll put a brown arrow over that. Nothing really is going on in that case. Okay, but then all of this should be equal to e to the 2x, so let's sneak that in over here. This is equal to e to the 2x. Now let's see if there's any cancellation, and there in fact is. Notice we have a 4z minus 2z minus another 2z, so this cancels with this, or with those two maybe I should say. Then one more thing happens. This z prime will cancel this 4z prime down to a 3. Then we can also divide e to the 2x from both sides, and that'll leave us with the following differential equation. Z double prime plus 3z prime equals the number 1. Okay. But notice this is a first order differential equation in the function z prime. We can see that clearly if we make another substitution, u equals z prime, and see what happens. So that gives us the differential equation, u prime plus 3 times u equals 1, which is a nice first order linear differential equation. We know how to solve these differential equations. So we've got a general formula, but I'll use the method of kind of guessing the appropriate integrating factor, which in this case will be e to the 3x. So if we multiply by e to the 3x, we'll have e to the 3x times u prime plus 3 e to the 3x times u equals e to the 3x. Now we can view this left-hand side as two functions being multiplied and then having the derivative taken. In other words, e to the 3x times u prime equals e to the 3x. Nice. Now we can take the antiderivative of both sides. That gives us e to the 3x times u equals, I'll call it c1 plus 1/3 e to the 3x. Okay, but now we can easily just multiply by e to the minus 3x and we'll have what u is. So let's do that over here. So we have z prime, which is equal to u, is in fact c1 times e to the minus 3x plus 1/3. Then last thing to do would be to take the antiderivative of that. So that will give us z. So z will be c1 over negative 3, but I'll absorb that into the constant. So it's c1 e to the minus 3x plus 1/3 x plus c2. But let's recall that y was e to the 2x times z. So that means we can write y as, let's see, multiplying through by e to the 2x, we get c1 e to the minus x plus 1/3 x times e to the 2x plus c2 times e to the 2x. Great. But now this is in a little bit weird of an order. Notice this stuff that I'm underlining in blue is the homogeneous solution. And then this thing that I'm underlining in green would be our particular solution. And of course, the particular solution is what we're going for, as the previous video talked about how to find the homogeneous solution. And now let's notice that this is exactly x times a polynomial of equal degree to the 1 in front of e to the 2x. It's a little bit cheesy here because there's just a constant in front of e to the 2x, and then times e to the 2x. So instead of something like this, what we'll have is x times something like this. Okay, so let's get that on the board. So the example we just did just motivates the following choice for the format of the particular solution to this differential equation that we've been working with. So let's look at it. Y of p equals x times e to the kx times q of x, where the degree of q equals the degree of p, if k is a single root of that polynomial. So up here, it was not a root of that polynomial, and we didn't have anything times e to the kx qx. If it's a single root, we have x times e to the kx times qx. So now let's see what happens if it's a double root. So this is a quadratic polynomial. So the only possibilities are a not a root, a single root, and a double root. So we've got the following example to lead us towards the last case of this setup. And that is y double prime minus 2y prime plus 2y equals e to the 2x. Now let's observe that the homogeneous solution is c1 plus c2x times e to the 2x. That's because the corresponding polynomial to this, which is r squared minus 2r plus 1, factors as r minus 1 squared. In other words, it's got a double root. So we're going to play the same game that we did before. We'll make a substitution. So let's make essentially the same sort of substitution. In fact, you can always make this sort of substitution and put everything in terms of this first case instead of looking at the second and third cases in the future if you'd like to. But just for completeness, we'll look at all three cases today. Okay, so again, let's substitute y equals e to the x times z. Notice that means y prime is e to the x times z prime plus e to the x times z. Derivative of e to the x is itself, so there's going to be a lot of e to the x's floating around in here. Then y double prime is e to the x times z double prime plus 2 e to the x times z prime plus e to the x times z. You pick up a 2 because you get this term from taking the derivative of e to the x here and the derivative of z there. Okay, so now let's plug that into our original differential equation and see what happens. So we've got y double prime minus 2y prime plus y equals, so we can factor an e to the x out. Our y double prime is then left at z double prime plus 2z prime plus z. Let's maybe put pink parentheses out that over there and then put an arrow to show that that's coming from that term. And then we'll have minus 2 times y prime, which in this case will be z prime plus z. Let's maybe put yellow parentheses there and put a yellow arrow to see where that's coming from. And then we have plus y, which in this case will be plus z. And just for good measure, let's put blue arrow over this. And then that's where that's coming from. And all of this needs to be equal to e to the x. Now let's see what cancels, if anything, in this case. And in fact, a lot cancels in this case. Notice that we've got a z minus 2z plus z. So all those z's will cancel. And then we've got a 2z prime and a minus 2z prime. So those are going to cancel as well. Furthermore, we can divide both sides by e to the x, leaving us with z double prime equals the number 1. Oh, I just realized that this should have been a 2 here, and this should be 2 e to the x, given our original differential equation. But that doesn't really change much. Okay, so z double prime equals 2. That means we can easily calculate z by taking the antiderivative twice. We'll get z prime is equal to 2x plus some constant, I'll call it c1, and then we'll get our original z is x squared plus c1x plus c2. Okay, nice. Now, y was e to the x times z, so that means we have our final solution y as x squared e to the x plus c1x plus c2 times e to the x. Great. Now let's see what we've got here. We have x squared times a polynomial times e to the x, where that polynomial has the same degree as this polynomial. In this case, it's 0. So that follows this pattern over here. We have x to the 0 for not a root, x to the 1 for a single root, and now we'll add here x squared for a double root. Now let's look at an example. We have y double prime minus 3y prime plus 2y equals e to the 2x times 1 plus x. And we can check that this number 2 is a root of the corresponding polynomial. 2 squared minus 3 times 2 plus 2 is in fact 0, but it's not a double root. But the fact that it's a root at all tells us we should probably look at the polynomial more in depth. So let's do that. So we're going to look at r squared minus 3r plus 2. Notice that factors as r minus 2 times r minus 1. If we set that equal to 0, we get roots r1, which is 2, and r2, which is 1. So in this case, it's a single root. the fact that it's a single root, we get a guess for our solution for our particular part. So that guess, yp, will be equal to x times a degree 1 polynomial, because this is a degree 1 polynomial, times e to the kx. So we've got x, a degree 1 polynomial, ax plus b, times e to the 2x. We can maybe write that as ax squared plus bx times e to the 2x. Notice here, that's why we have a x out here, because it's not just a polynomial of degree 1 higher, it's actually a multiple of x. There's no constant term here, and that's what we saw during our development of these strategies before. Now we apply, what's called the method of undetermined coefficients, which is what we've been doing, and that is we find yp prime and yp double prime, and then plug them into the original equation and set up a system of equations for a and b. So let's see, yp prime will be 2ax plus b times e to the 2x, and then plus 2 times ax squared plus bx times e to the 2x. So now we can combine like terms. We'll have 2ax squared, that's our x squared term. We have 2a plus 2b, so 2a plus 2b times x, and then we've got a lonely b, which is the constant by itself, e to the 2x. Then let's calculate yp double prime. So take the derivative of the polynomial first. That's going to be 4ax plus 2a plus 2b. Then we have e to the 2x plus the derivative of the exponential part. That'll pop a 2 out front. And then we'll have 2ax squared plus 2a plus 2b times x plus b. We have e to the 2x. Okay, good. Now we can combine like terms here. We have 4ax squared from this. Then we'll have 2a plus 2b. And then we'll have a 4ax here. And then a 4a plus a 4bx. So in the end, that'll be an 8ax plus 4b times x. Then our constant term will be 2a plus 4b. So we have plus 2a plus 4b, and then that's all multiplied into e to the 2x. Okay, so a lot is going on here, but now let's plug that into our original differential equation. We have yp double prime minus 3yp prime plus 2yp. Okay, so we can factor in e to the 2x out of the whole thing. And then let's look at our coefficient of x squared first. I'll maybe calculate that. So we'll have 4a, then minus 3 times 2a, so that's going to be minus 6a, so that'll be negative 2a. And then finally, plus 2a from this, so the coefficient of x squared cancels, which is really good news, because notice there's no coefficient of x squared over here. Now let's look at the coefficient of x. So that's going to be 8a plus 4b from this term, and then it'll be minus 3 times this term. Let's write it out so we don't make a mistake. So we have 8a plus 4b minus 3 times 2a plus 2b, and then let's see, plus 2, the coefficient of x up here is just b. Okay, so let's see, we've got 8a minus 6a, so that's going to be 2a, so we have 2a, then we have 4b minus 6b plus a 2b, so there's no b, so we have 2ax. So that's the coefficient of x, is 2ax. So let's maybe erase all of this calculation, and we'll just put that we have a 2ax in there for the coefficient of x. Nice. Now let's look at the constant term. So the constant term will be, let's see, for the yp double prime will be 2a plus 4b, then minus 3 yp prime, so that'll be minus 3b, And then notice for yp, there is no constant term. So that's good to know. So we have this is equal to 1 plus x times e to the x. Now we can equate the coefficients. So notice we'll get 2a equals 1, because that's the coefficient of x on the left-hand side and on the right-hand side. And then we'll also have 2a plus b is also equal to 1, because that's the constant term on the left and the right-hand side. So let's see. That means that in the end, we have a equals 1/2 and b is equal to 0. So we have b is equal to 0. Okay. So putting that into our original, that tells us that our yp is 1/2 x squared times e to the x. And then since we know the homogeneous solution, we can write down our general solution. So it'll be this particular solution, which we just calculated, plus c1 e to the 2x plus c2 e to the x, based off the fact that we have those two roots for our corresponding polynomial. Okay, so as you see, there's a lot going on here, but I think if you're careful and you remember the strategies over here and are, like I said, careful with your bookkeeping, these aren't too bad. I'll leave you guys with some warm-ups. So I've got 3 warm-up problems for you, and suspiciously there are 3 cases over here based off of our solution strategy. So the first is y double prime minus 5y prime plus 4y equals x squared e to the 2x. The second is 2y double prime plus 5y prime minus 3y equals 14x e to the minus 3x. And then finally, y double prime plus 6y prime plus 9y equals 3x minus 2 times e to the minus 3x. So your goal here should be to write the most general solution. So that means it should have a homogeneous part as well as a particular part. And that's a good place to stop.